Hello, happy Saturday. How are you today? Oh, hey Julian, how are you doing today? All right, I got some really cool problems for today. So let's get right started. The first one is, given n non-negative integers representing the histogram's bar height, where the width of each bar is 1, find the area of the largest rectangle in the histogram. All right, so this is super hard to understand without a picture, I think. So here's an example. The input is an array with these 6 entries. They're all non-negative integers. And you can think of these integers as representing the height of bars in a bar graph or a histogram. And you're supposed to find the largest rectangle, the area of the largest rectangle that you can fit into this histogram. So what I actually did yesterday real quick is I was using glitch.com. Super cool. You can make a website with even backend if you want, but I only just needed front end. And you can go, here's the edit project. So this is where you have your source code, my index HTML, and my script.js. And then you can show it live and you can share this link with anybody. So if you want, you can try this out right now. And what this cute little website does is it draws a histogram given an array. So if you give it some numbers, it draws you this histogram. So say we have the numbers 3, 4, 5, 6, 8, drop down to 1, 9, 5. Then this is the histogram we would get. All right, so we have an array, it represents a histogram, and we are now supposed to find the area of the largest rectangle that can fit here. So one rectangle you could fit is if you used one that is like flat on the ground, it goes all the way across all 6 entries, but it can only have height 1 because this one here is so short. So if you had the one all the way on the ground going all the way over, it would have area 6. Or you could have one that has height 2, but then it doesn't fit right here. So it would go from here over to here. Does that kind of make sense? And then that one would have width 4 and height 2, so area 8. And now the largest one you can fit in this particular input has area 10. And that is if instead of having it flat on the ground, we flip it upside down and we fit it here, including the second and third bar, or the third and fourth bar, depends on if we count like humans or computers. And then we can go all the way up to height 5. So we can get 2 times 5, which has area 10 in here. All right, so given a bunch of numbers that represent a graph like this, we're supposed to find the largest histogram possible. How should we do this? And this is a very typical interview question that you might get asked during the phone interview or the on-site interview. And ideally, your interviewer would give you an example and they'd also give you a picture, because without a picture, this is really hard to imagine. And especially if it's a phone interview, you can't share a drawing. Like, of course, you can have a piece of paper with you and sketch something for yourself, but you always want to show that you can communicate, and you also want to make sure that what you are drawing and communicating is right. So if your interviewer can't see that, that would be really bad. So if you get a problem like this in an interview, there's probably an image with it and an example input. All right, so how can we do this? So one option is we could take every element here as a starting point, and also every element on the right of it as an endpoint. So n times n starting endpoint areas, and then always find the maximum height that we can go to, so that's the minimum of the bars over that, and calculate the product of it. Should we do that? That's not a very fast solution, but it's a correct solution, it's pretty straightforward, and so at least you get something on the paper. And then once we have that, we also have something to test our answer against, because I only have this one test case so far. So once we have that, we can then think about faster solutions. All right, let's do that. All right. So const, I wonder if I should turn off the Quokka extension or if it's helpful. So const largest rectangle is a function that takes an input array and it's supposed to return the maximum area. Let max area equals 0, return max area. All right, so for let I equal 0, I less than 8 at length, I plus plus. And actually, I don't want to call it I want to be a little more explicit, so let's call it left. So for every left one, we also want to do, you guessed it, a right one, where right is left plus 1, right less than 8 at length, right plus plus. Let me just think whether this should start at the same spot. I guess it should start at the same one because you could have bars that just have height 1, right? Alrighty. Oh, hi Kai. I'm so glad I figured out how to say your name. How's it going? How's the weather in Germany? All right, so we're going from left to right, and now for every left to right, we need to find the height that we can use for a rectangle. So we need to find the minimum. Let minimum equals number just positive infinity. Oh, thank you so much. Every single time I get this wrong. Okay, that would have been very confusing because we would never run this loop. All right, so for let I equals left, I less than right, I plus plus. Less than or equal right, minimum equals mastered minimum of the old minimum and the height at that position. And then let area equals the minimum multiplied by right minus left. And I think I have to add 1 here. So because I'm starting, let's think this through. If we are on the nth element, on the last one, we still want that bar that has height 1, so I need to add a 1 here. And then of course the max area is method max of area and max. How does that look? So we take the array and we take every left point and then we take every possible right point. So we're taking every possible interval in this whole array. And then we find the smallest bar graph in that. Use the rectangle that fits over the length of this interval. It can't be higher than the smallest bar graph. We calculate the area and we update max area. Oh, hi Recursion. Well, your name's really fitting here. Welcome. I hope you enjoy this. All right, let's try it. Largest rectangle on this here. Oh, max is not defined because it is max area. Perfect. Console.log this. Perfect. So this seems to be quite correct. Should we try a few other examples? Let's throw in a 0 here just for giggles and see if the area really is 6. So let's draw this one. So what's the highest area we could get? We could go all the way up here, then it's 6, or if we go over here, it's 6 as well. Everything else is smaller. Okay, that looks good. What's another one? What if we go higher here? Let's make sure it goes all the way up to the top. So instead of a 6, I want an 8 here. And then, yep, the highest area would be this one. Everything else is smaller. Okay, that also seems correct. Anybody have a good array we should test? Anybody think we have some edge cases? Oh, I know one. Let's make sure the last one is actually used. Okay, I think this is being used. Let's make sure we have one. Yep, so if we go to the side, that also seems to work. Let's just double check the picture. I don't think this looks bad. Okay, so here the picture, we're going 2, 4, 6, 8, 10, 12, 14 should be the answer. Yes, that looks good. And I was trying this one here. All right, so this one's 10, 6, 8, 14. Okay, what's the complexity of this one? So we're going from left to right, that is linear complexity. But then inside this loop, we're also going from right to the end. So that is n times n, so we're already quadratic. But sadly, now we're iterating another time here over all those in the interval. So we have cubic complexity. So this one is O of n to the third. All right, so that's probably a little too slow. I mean, it worked fine on our examples here, but once you have something bigger, eventually it'll slow down. Well, I can't write an array out, but if we had like randomly generated one, so say we had 100 elements in the array, then the complexity would be 100 to the third. So 1, 2, 1, 2, 1, 2. I can't even read that number. So it would take 1,000,000 iterations. And if we had 1,000, it would be 1, 2, 3 extra zeros. So for n equals 1,000, this was already probably be quite slow. All right, can we make this better? So what's another way we could think about this? Another way we could think about it is if we take every bar by itself and we say, okay, this bar should be the height of the rectangle, what can we fit here? So what kind of rectangle can we fit here that has height 2? Well, only this small one. Now for this one, what can we fit here that has height 1? Oh, all the way over. What can we fit here that has height 4? Well, these two, then for height 6, it's just 1 bar. Here, what's the rectangle of height 2? Okay, so it's over of length 4. Okay, and then for height 3, again, it's a bar of width 1. So how would I code this, what I just said in my head? Well, I take every bar, I iterate over them, and then I go to the left and to the right, and I find the first bar that is too small, that is smaller than the bar I already have. And that gives me the left and right marker for that rectangle. I calculate the area, and then keep track of the maximum. And the complexity for that is not going to be cubic, it's just quadratic. So we already saved a ton of time because we started with a really slow solution. But this is much better than a cubic solution. We go through linearly, and then for every single one, we search the minimum on the right and on the left. Hi, Nuzdoska, thanks for the following. How's your Saturday going? All right, let's start over. So const largest rectangle quadratic, again, is a function that takes an array. And just like before, we have a max area, and we want to return that max area. So now the algorithm we had was we said we iterate over all the bars. So for let I equals 0, I less than a that length. No typo this one time. Thanks, Kai, for correcting me the first one. I would have been debugging for quite a while. All right. So we need to get the left one and the right one. But first, the height is a of I. And now, while let left is equal to I, so while left is bigger than 0, if a of left is less than the height, then we want to break. Is that right? So as long as we oh, and of course we have to move to the left, so left minus minus. So while it is bigger or equal to 0, and the same for right. So while right is less than a dot length, if a of right, if that is smaller than the height, we want to break. Hi to Maxi, thanks for the follow, much appreciated. No, I will not work on V8 on the stream. I'm not on the V8 team anymore. I'm on the GCP Google Cloud Platform team now. So there might be some GCP stuff. I also think, I would imagine that it's really hard to follow somebody working on V8 because you don't have a contained problem like in these interview questions. And you might also notice my font here is really big so that it's easy for people to see. And if I had anything more complex than an interview question, I couldn't work efficiently with just such a big font. I would need to have more information on the screen, and then I think it would just be really hard to stream that. I do believe there's some Firefox engineers, though, who stream some of their work. You should check them out. There's a few places, Firefox, engineer, live coding. Yeah, so Mike Conley hacks on Firefox stuff. If you're looking for streams to watch, there's Reddit, Watch People Code. Yeah, live programming streams, so some people announce their stream here. And then there's also, I want to say, Shipstream? Yes, Shipstream. So that's another website. Oh yes, and we're live right now, showing Shipstream. Shipstream inside Shipstream, awesome. Okay, yeah, but there's different people you can follow. And then of course, if you're on Twitter and you search for, what's the best thing to search for on Twitter? Like Twitch, live coding, also, yeah, this one here. Why does it not come up as a Twitter user? So, oh, weird. Okay, I was gonna say they work at Twitch. Maybe I misspelled the name. Emily Rose, they work at Twitch, and they can tell you about a few other coders. Hey, Ancient Coder, how's it going? It's still kind of morning here, but good afternoon to you. Streamception. Oh, Landra. Okay, thank you. Moralandra. Yes, so they work at Twitch and they a lot of times tweet about cool people that do live coding. So that's another way to find a few other streams. All right, back to work. So right is I, and we have to move right to the right to find the minimum. And now that we have left and right, we want to say the area is height multiplied by right minus left, and now just a few off by one arrows maybe. So this one is the first one that's too small, and this is the first one. Yep, those are both the first ones that are too small. So for this one here, the first one too small would be at index 1, and the other first one too small would be at index 4. 4 minus 1 is 3, but we only want width 2, so we have to subtract 1 here. And then we have to update max area is method max, max area, and area. Yeah, there's a bunch of design documents, there's blog posts. Mostly you just really have to dig into the code though. It's hard to get complex concepts into a readable design document and also stay up to date with the documentation. All right, so how should we test this? We can just copy and paste these test cases, and then largest rectangle, what did I call it? Quad, okay. And that still seems very correct, right? All right, let's make sure this all makes sense and why this is quadratic. So we're going through every bar, and we take the height for that bar. And then we set a marker at that same bar. And while we have space to the left, we keep moving left until we drop down from that bar. So here's the moving left. And we do the same to the right. We move to the right until we hit something that has 2 less of a height. And then the area is the height of the bar that we started with, and then right minus left, the space between those two, update max area. All right, so we went from quadratic, from cube to quadratic. So if we had 100 here, we would need 10,000. If we have 1,000, we would only need 1,000,000 iterations. Hi Ping Horse, the Go for JavaScript developers is happening on Tuesday in a week, on the 19th, I want to say. What day is today? 9? Yeah, so in 10 days. A little later, it's around 3 or 4 p.m., so it's 11 in the morning right now, so a few hours later. And I'm doing it together with Andy Bonds, who is on the Go team at Google. So very excited about that one. That should be fun. I've never done much Go. I think I've tried a few Hello Worlds, but never needed it, so never learned anything. But it'll be fun to work on that together. All right, so we have this. Let's just be good citizens and commit it. In 3 and can I have these symbols in a commit message? Oh, I can. Cool. Oh, cool. You're learning it right now. Do you also have a JavaScript background, or what's your background? Oh, okay. Yeah, cool. Yeah, those exercises are always a good starting point to learn. If you saw anything really cool or have a really cool extension or plugin or something, let us know in the next stream and we can see. Yeah, I would like to know about any tips. Thank you. Okay, so right now these tests here are very manual and they're also gonna start looking very messy soon. So why don't we write a test function? Let's write a test function that takes an array and it should compute let quad equals largest rectangle quad, let cube largest rectangle, if quad is not equal to cube, console log we want the array, and then quad is not equal to cube, and just make sure we see it, throw new error. And now let's call test. Cannot read length of undefined. Alrighty. Okay, this seems to work well. Should we just use random things here? Okay. Oh, okay, so as soon as I have a working array, everything's good. Okay, cool. Let's make another test helper random. Array is a function that should generate a random array of length n, and we want let a is an array for let I equals 0, I less than n, I plus plus a that push math dot random multiplied. Let's go with numbers up to 1,000. And how do I round something to a number? Do I just use math.floor, or is there like a no? Yeah, math.floor should be fine. So math.floor, return that one. So here we want to run the test of a random array of 20 elements. And I just want to see that. That looks like a random array, right? Looks good for us. Looks good enough, I'd say. Ooh, should we time? Should we time this? Like at some point, this should like stop printing here, right? Oh, now it's running. Okay, so this is where it's slowing it down. Should we print out how long it takes? Is this how I'm doing it? Console log quadratic for added length elements took after minus before divided by 1,000 seconds. I need to have smaller numbers here, otherwise Coco is going to get very confused. At least I think Coco will get confused. Before, after, cubic, for n elements took this long. Node, maximum rectangle, after has already been declared. Okay, that's not how I wanted my seconds to be. So we do after minus before, which should be milliseconds. Let seconds equal and we want master.floor. What am I doing wrong here? So before is the date, after is the date. Let before equals, yep. How am I getting these big numbers? Before, after, is there a typo in before and after maybe? Sorry, bot is deleting everything you wrote. Sorry about that. Oh, you say I should use performance.now instead of date.now. What's the difference between performance and date.now again? But this should also work. What's wrong here? Before, after. Oh, I see what's wrong. I see what's wrong. All right. Yeah, it's more precise. I'm sorry, Nightbot is the enemy. Okay, yeah. So that looks more like it. And now if we go up to, I think it was 20,000 when I started seeing problems. Or not problems, but like a noticeable slowdown. So let's see how long this takes. Yeah, in such a silly benchmark, it doesn't matter much if how precise it is, but it would probably be better if it's more precise. Date versus performance.now. What does Stack Overflow have to say? What's the difference? More precise in orders of magnitude. Okay, yeah. So it's probably good practice to just use performance.now for these things. Nobody has time to wait this long. Do we see a slowdown at 2,000 already? Oh, this is already quite, not quite slow, but a little slow. Let's try 10,000. Okay, 10,000 takes too long for my taste. Let's do 5,000. Binary search. Performance is not defined. Do I not have that in Node.js? Benchmarking advent of code was helpful, especially when you go for saving lines of code versus speed. I was just trying to go for correctness and not for speed. Performance. I probably misspelled performance, right? How do you spell performance? Oh. I need to require performance hooks, I guess. Okay. All right. Come on, don't be that slow. Why is it getting so much slower between 2,000 and 5,000? I think I'm a little bit too impatient. One Mississippi, 2 Mississippi. 1 Mississippi, 2 Mississippi. Oh, okay. So here you already see a big difference. The quadratic one still took 0 seconds rounded, whereas the cubic one took 4 seconds. So if we just go up by 500, maybe we see something. So big improvement from the cubic to the quadratic algorithm. 0 to 7 seconds. Okay, yeah, it's really slowing down with that cubic complexity. Okay, so we have good tests. We can even use random arrays. I would say let's commit this. Just in case. And what I want to do now is, so we have cubic, we have quadratic, let's go for linear, right? Right. All right, so how can we solve this in linear time? With the quadratic approach, we looked at every element, and then we iterated to the left and to the right for each element to find the next minimum on the left and on the right. That seemed like a lot of duplication because we always would iterate over the same elements. Like for this one here, to find the minimum on the left, you repeat the steps that this one did to find a minimum on the left. Or for this last part, it's more obvious. So this one here did 1, 2, 3 steps to find this minimum. And then this one here, oh no, the minimum is right there. But you could see how, so if we do 2, 1, 5, 6, 2, and then just have a bunch of 2's here, you could see how the effort for all of those finding this minimum seems like we're repeating the same problem, especially if you have like 3, 4, 7, 8. I'm so proud of my little tool here to visualize everything. Like iterating over all the bars and going single steps to find the minimum is very repetitive. And that's exactly where we can find some extra time. And I want to look at this as an extra problem first before we combine it. Hi, Deceiving, how's it going? Oh, I guess I could push my code so you have what we're working on right now. Okay, so instead of finding the minimum all the time, we want to pre-process the input array and generate two arrays, a left and a right array, where we have the min on the left and on the right. And we can forget for a moment about the rectangles and just do that here. So given an array of integers, find the nearest smaller number for every element such that the smaller element is on the left side. So const nearest smaller is a function that takes an array and it should return an array. So const result is this array. And now for let I equal to 0, I less than a that length I plus plus. So we want to fill this result here with the find the nearest smaller number for every element such that the smaller element is on the left side. Does that even make sense? Yeah, find the nearest smaller number for every element such that the smaller element is on the left. Okay, so how do we go about this? So for this one here, there's nothing on the left side. So the smallest number, we would just return -1, I guess. Now for this one, again, there's nothing smaller, so we would have to return -1. Let's go back to our default array here. Now for this one here, the smaller number of course is 1. For this one, the smaller number is 4. And for this, the smaller number is also 1. Now a neat trick you might have noticed is that as soon as we calculate the smaller number for this bar here, we will never ever need these large bars again when we're computing smaller numbers for anything coming on the right. Because why is that the case? Well, anything that's smaller than 4 will certainly not have things that are bigger than 4 as the smallest number. And anything that's bigger than the bar at 4 will stop at the latest on this one here. So since we can ignore certain bars once we've processed them, we'll use a stack to keep track of the bars that we're using. Hi NVDev, hello to Austria. Thanks for joining. So we need a stack here. And while stack.length is not 0, and we want to pop things from the stack as long as they are bigger than the height that we currently have. So let's write a pop function, I guess. A peek function is a function that returns. Thanks for the follow, NVDev. What's happening in Austria? How's the weather there? Do you still have a ton of snow? Forgot. Kai said the snow melted in wherever he is in Germany. So you want to return the last element, stack.length -1. Stack dot peek. If this is bigger or equal to the current element, then we're popping. Okay, and now if stack.length is equal to 0, that means there's nothing on the left. Oh, snow again next week. 11 degrees Celsius. I wish it were this warm. We are back to like 0 and it's super windy here. And if if something's on here, result that push, stack that peak. All right. So for 2, 1, 5, 6, 2, 3, console.log, and I call this nearest smaller of this array. Oh, that looks wrong. Okay, but what do we expect for this? So for the 2, we expect a -1. I'm just going to write this here. For the 1, we expect a -1, and then we expect a 1, a 5, a 1, a 2. Is that right? Smallest numbers. Smallest one is 1, 4, no, 5, and then for this one here, next smallest one is a 1 and a 2. Okay, so that's what we'd like to have. It's not quite what we're getting. We're always getting a -1. Because our stack here is always very empty. So stack that push. -1, -1, 1, 5, 1, 2. All right, so does that kind of make sense? So we're going through this array, and for every one we want to find the nearest left neighbor. We go through the array once, and we're building a stack. And since the stack has at most n elements, and we're pushing and pulling from it, but not more than pushing n elements in total, because we just push once for every element here, this is definitely linear time. So we can find the nearest smaller on the left in linear time. And now that we have this result, we can use it or we can use the same strategy in this algorithm here. So here we were going through every bar, that makes sense, taking the height, and then we were computing left and right by iterating over all the bars again. So instead of doing that, we want to use a stack now. So we use a function similar to this one. One problem with this one is it gives us the numbers directly, the height of the bars. It doesn't give us the indices. So let's change this to give us the indices. What should that be? So if we want the indices, then we always need to, so we're pushing just the index here. And that means we need to compare A of this index. And the same here when we're pushing, oh no, we want to push the index into the result. Right? We're comparing height of the index and we're pushing the index into the result. So let's make sure we get the right indices here. So we get -1, -1, this one has index 1. Now this one should have index 2, and then the 4 should have index 1, and the 5 should have index 4. -1, -1, 1, 2, 1, 4. -1, -1, 1, 2, 1, 4. Wait. That is, oh, this is 1, 2, 1, 4. Yes, 1, 2, 1, 4. That's what we want to see here. Okay, cool. So this function that gives us the nearest smaller on the left works. So let's copy and paste this and make our linear function. All right, so instead of quadratic, we want linear. Hopefully it's really O(n) at the end. So we keep track of a max area, and now we also need a const left nearest, which is nearest smaller of A, and we need the const right nearest. Okay, how are we getting the right one? Obviously, we could rewrite this whole function and reverse everything, or we could just use nearest smaller of A dot. Can I reverse an array like this? Yes, okay, A dot reverse. Okay, so that should give us the nearest one, but from the right. And then we have to reverse all of that again. Actually, I think I want to see that printed out for our example. Okay, so we take the height for each one, and now left, instead of doing this whole loop here, we can just say, well, the left one is left nearest of I, and the right one is right nearest of I. And we need to check if these numbers are correct. The next nearest one was one too far on the left. Okay, this should still all be correct. All right, so largest rectangle linear of our example here. Yeah, need to print the whole thing. Console.log, that did not go well. All right, so let's print out what we have. Console.log left nearest. Yep. Oh, this one needs another reverse. And for some reason the area is 12, so that's not quite what we want, because it should still be 10, right? Didn't magically get bigger. Okay, console.log right nearest. Let's have a look at the right nearest one. So what's the next smaller one for this one? Should be index 1, and then for this one it should be 6, and then for 2 it should be 4, for 3 it should also be 4, for 4 again it should be 6, and for 5 it should be 6. Okay, so this is what I would like to see. Why does this reversing not work the way I want it to work? So we reverse the array and we find nearest smaller. I see, because should we manually do the reverse? Well, not manually. Console.log nearest small, well, a.reverse. I can copy and paste 3, 2, 6, 5, 1, 2. All right, so this is what the array looks like if we reverse it. And now to the left, so we have -1, -1. I mean, that should all still work if we do the -1s here. So if we do nearest smaller of a dot reverse, it's this. And now the problem is, how do I go from these numbers? Okay, and then we're reversing it, which was this in reverse order. Shouldn't the left work just like the right, but we reverse it? Now we need to flip the indices though. How do we flip the indices? So we're reversing this. Okay, do we have to... All right, so the -1 should really be the 6. The 0 should be the 5. Like the indices here were all off. How do we flip the indices? Hey Mara, how's it going? So we are looking at this problem given a non-negative integers representing the histogram's bar height with the width of its bar is 1, find the area of the largest rectangle in the histogram. We just solved this in cubic time and quadratic time, and now we're working on the linear time. Linear time. And for the linear time, I'm using this nearest smaller function that's pre-processing my input, and it's generating this left nearest. So that works, and now I thought I could be clever and get the right nearest by just reversing the array, running left nearest, and then reversing the result. But since I'm returning the indices, my result's not quite what I want it to be, because now the indices are also reversed. And I'm not 100% sure how I'm reversing the indices, because it's not just addition to them. Do I need to have like a map of indices, or should we just rewrite this function to be like left and right? Nearest smaller left, I guess that's what we have to do, and then we can skip all this reversing here. Yeah, otherwise we would need a map, and that's like we would need a map that maps the previous index to the old index, and I don't want to do that, and it doesn't seem space sensitive. So we're just doing this here, the right. So we're going through from the end, while I is bigger or equal to 0, and subtracting I. While the stack is not 0 and the stack that peak is bigger, we're popping. That all still looks correct. Let's just run this. So if we do this initial array, the nearest one from the right, what are we getting? We get 1, 6, 4, 4, 6, 6. 1, 6, 4, 4, 6, 6. And we don't want to push -1, we want to push a that length. 6, 6, 4, 4, 6, 1, 6, 6, 4, 4. Okay, we're not quite there yet. Why would the first one be a 6? Oh, never mind, I'm going through those in the wrong direction. Result dot reverse. 1, 6, 4, 4, 6, 6. 1, 6, 4, 4, 6, 6. Okay. Okay, so we have the nearest. Nearest smaller to the right, and we get the right result. Okay. Oh, hi V. How's it going? I'm using this pretty neat plugin called Quokka.js. And that shows me everything right here, so I don't have to switch over to the console all the time. The only thing that's a little bit annoying is I can't copy and paste the things that it's showing here. But other than that, it's all good. Okay, so it worked in our test case. And let's think about this complexity again. So nearest, smaller, left, and right, they are in linear complexity. And then we're stepping through here linearly again. So we basically have like a 3 times linear, which of course is just linear. Okay, I'm excited to see how much faster this is and how far we can get. So when we ran this one here with 3000, we had to wait 4 or 5 seconds. Yeah, you can see Quokka is working now because there's no dots here. Might be that we have to switch to the console for that. So if we do node maximum rectangle for the 3000 elements, it should take around 4 seconds for the cubic one. Yeah, 0 and 5 seconds. So now I want to see how that goes with the linear one. So where's the test function? Test here. So instead of this cubic one, I want largest rectangle linear. Let's push all these tests to the end. Okay, so this random array function, we don't need to look at that. And then this is the test function. Kind of don't really need these. Oh yeah, so the nice thing is if we do the linear cases, yeah, let's run this for linear just to make sure. We do this for linear, yep, the answers are correct. And now since this is linear, if n is 1,000, we'll only need 1,000 steps, which is much better than 1,000,000 or 1,000,000,000 here. Cool. Okay, so it's correct for the small ones. A test function here takes quadratic and then linear, and it prints those out. And they all take 0 seconds. So let's challenge this a little bit. 10,000 should still be 0. Okay. Yeah, and remember how we couldn't even run it for like 5,000 with the cubic one because it was so much slower. Okay, this is starting to take a little bit of time. Exciting. Let's see how long this takes. Yeah, so this is why the interviewers, or like why in general in computer science this concept of asymptotic complexity is so important. When you implement, hey Vindicator, how's it going? Where are you joining us from? When you implement a solution in a quadratic complexity and one with linear complexity, just by using a few different inputs, you can actually see what a difference it makes. This one seems to take too long, so let's take half of it. Might still be too long. Ooh, from Britain, nice. So it's already Saturday evening. Doing pretty well. I'm a little bummed that it's so cold outside again, but I'm gonna stay inside where it's nice and warm. Do I have a 0 too many here? Is that why it's so slow? Okay, so 1 euro is fine. I can't even read that. 1, 2, 3, so 1 million. So if we go up to 1.5 million. Oh, then we have to wait for it. Hi Stan Shanpike, thanks for the follow. Okay, so this already took 2 seconds. Now let's go up to 2 million. Linear solution. Yeah, so obviously you can really stretch that. 2.5 will probably take like 8 seconds now. So with the linear part, 6 seconds, we can really run this algorithm for much larger inputs. I've lost a few zeros on the way. Okay, cool. I like this. Okay, yeah, 8 seconds versus the other one still just took a fraction, a few milliseconds, less than 1 second. I'm rounding here, so it looks a bit weird, but cool. All right, yeah, so that was the largest rectangle that you can fit under a bar graph. The program explicitly specifies that it needs to be integers, but all of this should work just fine if you use decimals here. In fact, we can do that. We don't need this long one, but if we do 2.2, 5.7, like the test still passes. We don't get an error thrown, otherwise my test would throw an error. And we could also try this one here. If we had 5.3 and 6.7, yep, we expect a 10.6 here. And now we get a different number, I guess, because we can do, yeah, let's just print it. I'm so excited about my little graphic here. So here the highest one we fit between 2 and 3 would be 5, 3, 10.6, but here we get 3 times 4, like almost 3 times 4, which is almost 12, so that's why it gets bigger as we increase this one. If you take this down, yeah, then it's still between these two. Okay, cool. And you could even make this work for negative numbers. Wait, could you make it work for negative numbers? Let's draw something negative here. Oh, so negative. I guess you would have to pre-process the array and split it up into chunks, because whenever you have this kind of crossover, you can't fit a rectangle, so you would have to split it into chunks and then just run the linear algorithm on the chunks. So here you'd have the maximum here. Yeah, okay. So the problem would be a little different, but the complicated part about getting a linear solution would stay the same. You just have to pre-process this into smaller chunks where they're all positive or all negative, and then just work with the absolute value from there. Alrighty, on to the next problem. Okay. Surprisingly, again, we're given n non-negative integers representing an elevation map where the width of each bar is 1. Compute how much water is able to trap after raining. So very similar looking problem. Again, we have non-negative integers, an array of them, and they represent an elevation map. And now we are supposed to figure out how much water is being trapped after raining. So if we draw this one, this is our elevation map. And one thing we could do here is we set this to 100%. Oh, I need the same impact. Okay, yeah, maybe this is easier to see with 100% instead of the 97%. So if it rains, where would the water be trapped? So on the left here, water would just flow out, I guess, into the ocean or whatever, but it wouldn't be trapped here. But then if it had rained here, we would have water trapped at index 2 of height 1. And then over here, there wouldn't be any water trapped, but there would be water trapped here between 4, 5, and 6 at height 2. And then there would also be some water right here. So we would have 1, 2, 3, 4, 5, 6 square units of water. Let's see, yes. So that should give us 6 units of water. So water is a function that takes an array, and it should return the amount of water trapped. Okay, so how can we do this? This looks a lot like the problem we just had, right? We also had these bars, and we were supposed to like fit something in these bars. And we came up with a linear solution by using stacks. How would we do this here? First of all, what's a naive approach? We could iterate over all the bars, and for every bar we have to figure out what the height of the water is there. And then, so here, for example, at index 4, the height of the water is 2. It can't be higher than 2, it'll flow out after 2. So we would take 2 minus the height of the bar 1, 2 minus 1, there's 1 water unit trapped here. So we could do that, right? Now, how do we figure out the height? If we at any point, we would go to the left and find the maximum bar, and we would go to the right and find the maximum bar. And then of those two maxima, we would take the minimum for the height, right? So let's just naively do that. And before we do that, what's the complexity? We're iterating over all the indices, and for every index, we go all the way to the left and all the way to the right. So it would be quadratic. All right, for let I equal 0, I less than 8 at length, I plus plus. Let left maximum equal 0 for let j equals I, j big O equals 0, j moves to the left, left max is mastered max of the previous max, and a of j. And I guess we should start 1 left of j, right? Otherwise the maximum would be the thing itself. It doesn't matter too much. And then we also need a right maximum. So for j is 1 to the right, while j is less than the length. And we're updating the right maximum. Let height equals math min of left and right maximum, and then water plus equals the height. Now let's call this water height minus the height at that thing. So we're calling water on this input, and Croker doesn't print anything out because I haven't turned it on because we're in a new file. Okay. Oh, assignment to constant variable. Water, water, water. This is just W. Okay. That did not quite work out yet. Let's see what we did wrong. One, 2, and 3. 1 is the maximum, 2, why would it say 2 and 3 instead of 3 and 7? Oh, because I'm putting in the height. I don't want to... No, I want to put in the height. Yeah, so the height is 0, 1, 2, 3. Three, 2, 1. For all of those, it is 3. For these, it is 2. Oh, and for this one, I'm thinking it is 1, but it really should be 0. Oh, yeah, 1. Okay, I see what's going on here. So I'm taking the water height, which I guess is correct. So 0, 0, but then here I'm adding negative numbers to it if the height was less than the maximum. So it might be better if we're starting. Yep, now it works. Okay. So the water trapped in this array has area 6. And this algorithm here is quadratic because we're iterating over every element, and then again we iterate twice, but that doesn't matter, that's just a constant factor. But then again we iterate all the way left to right. Okay, but at least this is correct. So how do we get this down to linear time? What's the repetitive part here? For every bar, we're going all the way to the left and all the way to the right to find the maximum. This looks a lot like we could pre-process it and do it once and then just access it. In the last problem, where we were looking at the largest rectangle, we were using a stack in a smart way, so we could get this pre-processed of the next nearest smaller one in linear time. But this one's actually easier, and if you try to do it with a stack, I think it gets very confusing. Like, there is a way to solve this with stacks, but it's not really how I think about this. When you're using stacks, you're kind of looking at levels of water, so you like figure out, oh, there's like 1 here, and then there's 3 here, and it's just, I don't know, I think it's more complex. Hi, Fainasic bro. How's it going? And also, hello girls and non-girls or guys. Hello everybody, I guess. Oh yeah, we're doing common interview questions. That's the whole point of it. We want to do the common ones. Most interview questions, like, there's a few tricks or concepts, and then any interview question is just a variation of that. Like, it's either a cute little story like water, or it's some sort of variation, but it's always similar tricks. It's like pre-processing, so you have something in linear time, use a stack, use a queue, use a hash set as a data structure, use sums for something. So once you've seen a bunch of these tricks or concepts, you're hopefully able to, when you get to the interview, recognize what kind of concept will solve it. Yeah, I'm sorry, little doggy is barking, but now he's sleeping again. He's a pretty good dog, I have to say. He's very good. All right, so how do we find this array of maximums to the left and to the right? I think it's pretty easy, and I want to say the array is just that thing here that we already got printed. So let's just write a function for that. So const left max as a function. Oh yeah, he wanted to say hi too. He's a shy doctor. He's not like a Twitch star, so he doesn't want to come on the show, I guess. Yeah, I guess he heard the hi guys and he just wanted to say hi back. Hey Bill one, yes, we did finish the maximum rectangle. We did it in cubic time, quadratic time, and in the end we did it in linear time using a stack to get this array of left and right nearest, like the index of the nearest smaller on the left. And now we're doing a very similar problem but with a different solution. Similar in the sense that we are using both times this like histogram graph here. Yep, you can always rewatch it. All right, so how are we getting this array of left max? So we want to return an array here, and I guess, not surprisingly, we iterate over a, so I equals 0, I less than a dot length, I plus plus. So for every element, is it easier if we start with the rightest maximum? No, it's not. So what's the maximum on the left? For the first one, the maximum is 0. And then for the next one, the maximum is itself. And then, okay. M of I is equal to method max of maximum and A of I. So that's what's happening. Log, console.log. Oh, duh. And okay, I got it. I don't need a maximum. I can just always use the last one. So M of I is A of I minus 1. No. M of I minus 1. So the maximum is 0. Now I take max of I is the maximum of 0 or 1, so it should be 1. And now I'm taking the max. Why does this not work? Oh, this is silly. Duh. Okay, 0, 1, 1, 2, 2, 2. Yep. Okay, that looks good. Now, how do we do this for the right? Do we need, just like before, do we need a function that goes through in the other direction, or could we reverse the array? So if we reverse the array, I think we could just reverse the array. All right, so let left max is equal to left max of A, let right is equal to left max of A dot reverse, and then for everyone, instead of this other for loop here, I can just take left of I, and I actually want to call those lefts and rights, because there's more than one in them in the array. Okay, it's not quite right yet, because I think what I did here is, so I'm reversing the array, I'm finding the max, but then I have to reverse it back, right? No, we lost some water, shoot. Okay, well, before we play with the reverse, let's make the write max. So I is equal to a.length minus 2, while I is bigger than 0. And we want to go smaller here. And here we have the one that's one bigger, the one that's on the right. Okay. And let's print write max. Okay, that didn't work because we need to initialize this differently. So maximum of max, that length minus 1. The last one here is equal to 0. And then we let I start one smaller than the last one. And we're setting it. Okay, what is wrong here? Maximum is an array, and we set the last one, which is a.length minus 1. So we get 3332220. Does that look right? The maximum on the right is 3, and then for those it's 2, and then for this one it's 0. Okay. Or should the last one be a 1? I guess the last one should be a 1, so it should be a of a.length minus 1, whereas this one should be a of 0. Yep, and now it's 6. Okay, I needed these numbers here because when I'm calculating the water height that I'm adding, otherwise I would have a negative number. Yeah, okay. All right, so instead of using this write max, now that everything's correct, let's do left max, but reverse this, and then reverse it back. Okay, yeah, this seems to work. Oh, why does this still say squared? It's just O of n. Okay, so to me personally, I guess the trapped water looks just as hard as the maximum rectangle, because this one is equally hard, and then it's hard to figure out where the water stops. But then when you think about it a little more, it's actually somewhat more linear, because you just need to find the maximum on the left and on the right. For the histograms, you didn't need to find the maximum, which would stay the same no matter how far you moved, unless you moved over that edge. For the histogram, you had to find the next smallest one, which I thought is a little harder. And that's also why the histogram, you can't solve it in this linear without a stack. It's easy to solve in a linear fashion with a stack. With this one, you don't need something as complicated as a stack. You just go through this here very basically and find this pre-process this array that gives you the maximums on the left. It's just keeping track of the maxima you saw and only get bigger. And then doing that first, it's easy to find a linear solution here. Okay, yeah. Unfortunately, I don't have a ton of time today. I have a bunch of errands to run. So I think 90-minute stream is good here. What did we change? Oh, okay, we just commented that out. We put decimals in. So let's water trapped linear solution for trapped water problem and dash the other ones. All right. Hi, Bilby1. Nope, I don't feel like doing this with no extra space. So it's a good question though. I guess that's like homework for everybody. Yes, unfortunately I have to leave. But if you paid attention here, we had to allocate this lefts and rights arrays, so we needed extra space. And we can actually get away without doing that. If you want to try it out, think about like moving 2 pointers in from left and right. That's probably the most helpful. All right. Or maybe Build1 wants to solve it on stream and you can watch them. Okay. All right. Thanks, everybody. Thanks so much for joining me. I hope you have a great rest of the weekend. Unfortunately, next Saturday I'm traveling, so no stream on Saturday. But we have a bonus stream coming up on the 19th. Oh no, I'm gonna be seeing myself. Oh no, I'm gonna see advertisement. Okay, so on the 19th here, I'm coding together with. Why is this Kristen? It's together with Andy. I'm coding together with Andy. He's an engineering lead for the Go team at Google and will do Go for JavaScript developers because I'm a JavaScript developer. And he'll show me what to do. So that's on Tuesday the 19th. Tune in for that. I won't be here next Saturday, but in 2 weeks again. All right. Thanks so much, everybody. I hope you had fun. Oh, and if you were wondering, I was using Glitch to quickly make this cool thing so I could see my histograms. It's Google Charts, and then I'm just using Glitch where I don't have to worry about where do I host it, how do I run it. It's all here. And the cool thing in Glitch is you can go to any project and remix it, so it's kind of like a Git clone, except that it's up and running right away. So if you want to make this a little more beautiful, if you want to add the water to it, that would be a good one. Go do it. If you did, send the link to me on Twitter. I'd love to see it. All right. Thanks, everybody. Hope to see you Tuesday in a week. Have a great weekend. Bye-bye.